Okay, matrices for map combinations. So let's say that you have two maps, like say F that goes from V to W and G that goes from V to W. Then there's another map, F plus G, that also goes from V to W, and it's defined like this. The action of F plus G on a vector that's in V equals just the sum of the images. So it turns out that if F and G are linear, then then this one is also linear. So this is now it turns out if you ask, well, what about the representations? Like we know that F is going to have a representation F, and G is going to have a representation G, and then it turns out that the representation of F plus G will just be F, just be the sum of the matrices. And this is although here to form the sum, they both have to be from V to W. And here, this only makes sense if they're the same size. Like they don't have to be square matrices. This could be 2 by 3, but then this one has to be 2 by 3. So they have to be the same size matrices. So it all goes over. And then, so for example, if you act on a the one thing is that to form these representations, say F and G, you have to have chosen a basis, right? So let's say you chose basis B for the domain and basis D for the codomain in each case. Then this one, F plus G, is going to be the representation of F and basis G, and G will be the representation of map G and basis B. So that this will also be, basis B to basis D. These are okay. I'm not sure the original author used B and D for bases. I'm not sure for the domain and codomain, and I followed along, but I'm not sure exactly why he chose B and D. It's okay, but so this is a way of combining maps to get new maps, and you end up with the representation being what you already know about in terms of sums of matrices, and the same thing works if you want to multiply a number by, if I take a map and say there's another map that's like 5 times that map, that's going to have the same thing. You're going to multiply it by a number here. So the interesting case then is composition of maps. Now, I don't think we went over exactly compositions, but here's the idea. If I have a linear map for F from V to W, and I have a map G from W to X, vector space X, say, then how does V act? Well, F of any vector in V is going to produce some vector in W, right? So W is the image of V under. So this is sort of the functional notation. You put V in, you get W out. Now G is defined the same way. If I take any vector in W, it's going to give me a vector X out. So I put in W and I get out X, a vector in X, okay? So there's a map that allows me to combine these two, which is now which you can see here that the map is called G circle F, and what this is going to do is it is going to act from V and go to X. So you see, it's left out W in the middle. Now this only works if the code if F goes to W and then G starts in W, these have to be the same because otherwise the composition wouldn't work. This is called composition, right? Now, how is composition defined? Well, the important thing here is that even though I've drawn F on the left here and G on the right, Fx first and Gx second. So you read it from right to left. Okay, so what F starts with V. So how it's defined is defined as G of F of V. Okay, so it takes the rightmost one, and that acts first. Okay, now F of V produces some W. So this is going to equal G of W, and G of W produces some X. So it's like a relay race. Okay, now just to in case this is to slow down and be, let's say we take this is an aside on composition, just so you understand. I mean, you've got the vectors here, but let's take a simpler set. So let's take like 1, 2, and 3, and A, and B, 4, 5, 6, and C, B, 7, 8. The sets, set A, set B, and set C. Then F is going to take 1 to 6, 2 to 5, and 3 to 4. And B is going to take 4 to 8, 5 to 9, and 6 to 7. So this is G. The arrow diagrams here tell you what's going on. So you can see here that F of 1 equals 6. And then G of 6 equals 7. So that enables to say that F circle G of 6 equals F of, not F of, sorry, wrong way around. See, F in this diagram here, Fx first and G second. So you write G circle F of, say, 1, which is going to be defined to be G of F of 1. But F of 1 is 6, so that's G of 6. And G of 6 is 7. So, so as a result, from this relay race kind of thing, you can see that from A to C, G circle F acts between 1, 2, and 3, and 7, 8, and 9. So it's going to take 1, right, to 6 to 7. So 1 goes to 7. 2 goes to 5, goes to 9. So 2 goes to 9. And 3 goes to 4, goes to 8. So 3 goes to 8. So this diagram here is just how it's defined. This is the map that results down here. Okay, so this is just a concrete case to show you, like this is sort of abstract here because we can go through this with particular vectors, but the same thing is going on with composition here, right? Okay, so that's the end of the aside. So composition, does this make sense to you guys? Composition? You're used to this in pre-calculus and calculus in the following sense. If I had F of, these are real numbers. This is just functions, right, from real numbers, from R to R. So if F of X was X squared, and G of X equals, let's say, 2X plus 1, right? Then the thing is that since these are both functions from R to R, I can compose them so that when you did this in pre-calculus or calculus, the compositions didn't, the domain and codomain were generally like R and R. Maybe there was some restriction, but they were generally all made sense. You didn't have to worry about that. You could just put, so then you had the composition G circle F of X was equal to G of F of x, the same definition, but that equaled g of, what was f of x? That was x squared. And g of x squared equals 2x squared plus 1, because I put in whatever g of x, if I put in the, these are just placeholders, so they aren't really the same x and here and here. This could be like x1, x1, x2, x2, right? So you can see, okay, so you did this in pre-calculus where you'd compose two functions, and then you could also do it the other way. You could look at f circle g of x, and it would be defined the same way as f of g of x, and then that would be f of, and then g of x would be 2x plus 1, and then f of that would be 2x plus 1 squared. And you can see that these aren't the same thing, that these are not the same function, right? So, and you dealt with this in various ways for some reason in pre-calculus, because then when you had compositions, in calculus, you had to take the derivatives of compositions, right? So that was where that came from. This is also an aside, just telling you that you've seen compositions before in different contexts. So here, the question is, if I'm given f from v to w and g from w to say x, and so I have the composition g circle f, right? Then the question is, well, if f is the matrix that represents f and g is the matrix that represents g, then it turns, you can see that what's going to happen is, if let's say that this is, v is n dimensional and w is m dimensional, then w is m dimensional, and this is, say, r dimensional or p dimensional, okay? Then this is an n by m matrix, and g is an m by p matrix, right? Well, it turns out then that the representation of G circle F is just the matrix GF. I mean, other way around. Yeah, it's just going to be F. No, you have to act with F first. Yes, let's see. Yeah, it has to be FG, right? Because, no, what am I doing? Yes, it has to be, yeah, I think the point is that you want, for some reason, this is, okay, so we have here G circle F, Fx first, but I want, okay, so let me just as a sanity check, let's go back and look at the text to make sure that that whatever was going on in my mind that was bothering me is notation. So here's the sum, and then scalar multiplication, sums and rescalings. We talked about that, the zero map. Let's get to composition down here. Composition, the composition of linear maps is linear. That's nice, and it. So here you have, it's going through and defining matrix multiplication. Okay, the composition of linear maps is represented by the matrix product of the matrix representatives of those maps. So here is the arrow diagram. Something was, so in this situation here, you can see that we've got V and H. The map H is taking you to W, and then G is taking you from W to X, and that's actually maps to this V to W to X here. So we have, except they've called this H and G. So let me change this name here so that it's going to be exactly the same, and we'll so we have H here, and then this one will be H, okay? And so we have the map. We obviously want H here to act first. So we have the composition G circle H, right? And then so it must be okay, so they want the representation to be here G and H. Okay, let's go back and maybe what the issue was, maybe the assignments of, let's do a concrete case to see, because I'm getting myself, so what I was telling you was correct, that H is the representation of H, and so it has to act first and then G. But let's see what the dimensions of H and G are, so that if H takes you, say, from, let's say it's a map from R2 to R3, and G is a map from say R3 to let's make it RST R plus S plus T to R4, right? Then H is going to be a right. What is H going to be? This is like R2, and this is R3, right? So it's going to act on two-dimensional matrices. So it's going, so the point is that the matrix that represents H is not going to be 2 by 3 dimensional. That was my error. This one's going to be 3 by 2 dimensional. Because, well, it's because the point is, how do we define this matrix H? Well, it's the image of each of the vectors here, right? So we're going to have 2 columns, one for each of the unit vectors here, 1, 0, 0, 1, but each of the columns will be 3-dimensional. So that was the intuitive thing the error that I made was this one H here is not M, is M by N dimensional, and this one is P by M dimensional, which makes sense here because then G is P by M and H is M by N, so they can be multiplied. What bothered me before was I had written this the wrong way around and written this the wrong way around, so I couldn't multiply the matrices the way I knew you should. So that was so the point is, when I make a map from the dimension here to the dimension here, let's put here, here's your matrix H, and you have a column here, right? So the number of columns is the dimension of the domain, right? Because I'm going to have 2 columns here. So I'm writing this as row and column. And so the number of columns, I'm going to get 1 column, and each column here, the number of rows is the dimension of the codomain, okay? Because we've done this implicitly, but we just haven't brought it out. So because if I was to find the matrix for this map, it's going to be here 1, 0, 1, because I take 1, 0 here for the basis action, 1, 0, that's be 1, 1. Then the y will be 0, 1, will be 0, 1, 1. So here's the matrix. Here's H, a 3 by 2 matrix. Okay. Then over here, for G, what would it be? Well, G is going to be, well, we're going to have 3 basis actions here. So that's going to be 3 columns. So this is going to be 3 and this is going to be 4 because this, the dimension here, dimension of V is 3 and here is 4. So if I put in, to actually do this, 1, 0, 0 is 1, 0, 0, 1, 0, 0, 1. Then 0, 1, 0 would be 0, 1, 0, 1. And the third one, 0, 0, 1, would be 0, 0, 1, 1. But this simple map, so I can just do it quickly. So now you see that I can map then. It makes sense to map. You can't, so that this is a 3 by 2, and this is a 4 by 3, so I can map with H and G because it's a 4 by 3 times a 3 by 2 matrix. And this fits because if I act with H on a vector, H is going to act, if I take the product here, H would act first, then G, which is what happens in the composition up here. Okay? So I think that we didn't really focus. I didn't really sort of make that salient, and then I sort of went over and said, "Oh, well, this is sort of a common thing." You sort of think that this is the problem with compositions, is that because you usually draw the F on the left and then G, this is the reversed. It's the reversed order. Because you've done F first, we often draw it on the left. And down here, the same way that occurred, that you sort of think of, oh, well, when I write N times N, right? This is, you think, well, here's N and M, so shouldn't it be an N times N matrix? So it turns out that if you have a map from an n-dimensional to an m-dimensional space, the matrix that represents it is going to be m times n-dimensional. So you reverse the order of the dimensions to get the dimension of the matrix.